This is Angela Galloway, and this is a lecture recording for STA220. We are in Unit 5 now. This would be Unit 5, Chapter 9. This session's probably just going to cover 9.1. We only have two sections in Chapter 9, 9.1 and 9.2. One section is going to cover proportions, and the other section will cover means, similar to how we did in Chapter 8. You know, we kind of broke it up into proportions and means for the sampling distributions. So before we get into that, I just want to look kind of a quick review of what we've done so far and how we're going to use that to continue to move forward for these last two chapters. So one of the very first things we learned about in our class was statistics and parameters, okay? And those are still going to be really important, knowing when we're talking about a sample, so our data is, used to calculate a statistic, or knowing when we have a population and the data is used to calculate parameters. So remember, statistics come from samples. So some examples of statistics are X bar and P hat, okay? Parameters come from the population, so that's our mu, our sigma, and our p, okay? Inferential statistics. So we looked at how when we have a sample, we can use that statistic from the sample to infer about the population parameter, right? So inferential statistics is really what we've been doing from chapter 7 on, is we've been looking at, I've created this sampling distribution or this distribution of data. I want to look at my observation and see how it looks compared to what the population's supposed to be, and then I'm going to try to infer something about my sample. Is it showing that my sample comes from a population like I thought it did, or does it maybe come from another population? So that's how we're using inferential statistics. Then we talked about sampling error and the need to do randomization. So we do simple random samples, but we said even when you randomize and take large samples, you're still going to have that sampling error that always occurs because you're taking a sample. You're going to have some deviation from what the true population parameter is. We learned how to calculate means and standard deviations, also how to calculate proportions. So of course we're going to be using those processes going forward. Then when we came back for the second half of the semester, we've been talking about the normal distribution, right? And how important it is. It's especially important once we start talking about the sampling distributions. We saw that even if the original population wasn't normal, that our sampling distributions would be normal, right? As long as we had a large enough sample size. So thanks to the central limit theorem, we learned that we needed n to be greater than or equal to 30 if we're working with sample means. If we have a sample size greater than or equal to 30, then the sampling distribution of our sample mean is going to be normal, right? For proportions, it was a little different. We just needed n times p times 1 minus p to be greater than or equal to 10, and then that would give us the evidence we needed to say we could use the normal distribution for the sampling distribution of p hat. All right. Now, when we got into chapter 8, you may have wondered, why do I need to learn about sampling distributions? Why couldn't I have just stayed in chapter 7 where we were looking at just normal distribution, so just data that happens to fall into a normal distribution, right? So why couldn't we just stay back in chapter 7? Well, the first issue is it would be okay if every population was normal, but we realize that they're not. I mean, we've shown several examples of populations that are skewed, or maybe or have a uniform distribution, or have geometric or Poisson or all these other distributions we didn't even get into. But there's other distributions out there that data falls into, which is okay. I mean, if we know they fall into another distribution, there are some formulas we can use for them. However, the normal is much easier for us to use. So if we can show that even though the original population wasn't normal, the sampling distribution is, then we would probably rather work with that sampling distribution. The other thing is, most of the time with inferential statistics, we are looking at a sample mean or proportion and trying to see if it's different from what we expected, okay? So you're usually not just looking at a single observation, you're looking at a sample mean or a sample proportion. So like, for example, let's say you're investigating a new drug that claims to decrease blood pressure in patients that have high blood pressure issues. Would you try the drug on just one person and see if their blood pressure was lower than the average? Or would you take a sample of 30 patients with high blood pressure, let them try the drug, and then see if their mean was lower than the expected? Well, obviously, we would probably take a sample of people, right? We're probably not just going to look at how it affects one person. So once we start taking a sample, then we are in the sampling distribution when we get our data back, okay? And so that's generally what we're going to be doing. So what do we have left to do? Well, now using everything we've learned up here and thinking about how we use inferential statistics, we're going to try to figure out how to determine if our statistic is different from what we expected. Okay, now our statistic is probably going to be different from the true parameter. We said because of sampling error, um, we're going to have a statistic that may not be exactly equal to the parameter, all right? But what we want to see is the difference that we see in the parameter and the statistic just due to sampling error, okay? Or is our statistic different enough from the parameter to say that our statistic is special? And so we think the parameter is not really true. Okay, so either it's increased or decreased or something like that. Okay, and so that's what we're working towards in this chapter. So chapter 9 is all about estimating the value of a parameter. So inferential statistics, trying to figure out what the true parameter is. So estimating a population proportion is what we're doing in 9.1. Okay, so we have a new term in this chapter. It's something we've actually been using, we just haven't called it this. So what we're going to talk about is a point estimate. A point estimate is the value of a statistic used to estimate the parameter. So our point estimate, the ones we've been using are X bar or P hat. Okay, so those are 1 point, okay, 1 point on the number line that estimates what we think the true parameter is. Okay, so it's really just our statistic that we use to estimate the parameter. Okay, so it could be our X bar or our P hat. So suppose we want to estimate the proportions of Americans who would prefer balancing the federal budget to cutting taxes. We obtain a simple random sample of 1,000 Americans and 550 of them said they prefer balancing the budget to cutting taxes. Okay, so what would our point estimate be? Well, we're trying to estimate the proportion of all Americans, okay? So we're looking for trying to estimate the true P, right? So we're going to use a P hat here. That will be our point estimate. We'll take 550 divided by 1,000 and we get 55% or 0.55. What can we infer from this statistic? Well, we expect that 55% of all Americans prefer balancing the budget to cutting taxes, okay, right? Because we're using that inferential statistics to take our stat and infer about the parameter. If I took another sample of 1,000 Americans, would I expect my point estimate to be exactly the same? Probably not. I mean, it's possible I could take another sample and it be exactly 55%, but it's probably more likely that I'm going to get something like maybe 54% or 56% or 55.5% or whatever. Now, I'm hoping that it's going to be close to what my sample said, because then that gives me a little more evidence that maybe the true parameter is close to that number. But every time I take a sample, I'm getting a different group of people, right? So I'm going to get probably a little different answer, and that's due to sampling error, right? Okay, let's look at some examples of things that have happened that maybe weren't what we expected, or maybe people just didn't really understand how to read some of these proportions, okay? So whenever we're taking samples, we are calculating point estimates or statistics to try to figure out what the true parameter is. Now, why are we unable to just find the true parameter? Well, remember, to get the true parameter, we have to survey or question or whatever the entire population. It's difficult to get data from the entire population, right? So instead, we take a sample. We hope that sample is representative of the whole population, and then that sample will give us a pretty good estimate of the true parameter. Now, this example is going back to fall 2014, so it's a little old now, but it's something that has still been talked about even pretty recently with the recent elections. They kind of referenced some of the fact that, polls can't always predict what's going to happen. So what we saw here, this was when McConnell and Allison Grimes were running against each other for the Kentucky Senate. And of course, it was a big deal because McConnell, is the Senate leader. And so it was going to be a big deal if he was unseated. So, and of course, he'd been there for a long time, and it's always a big deal, Republican Democrat thing. But this was a bigger deal just because McConnell is such a big Republican in the Senate. All right, so looking at this, we had these different polls. Okay, so looking back here, we saw on October 10th, which was about a month before the race, this poll showed that 46% were going to vote for Grimes and 44 were going to vote for McConnell. Now this was kind of a big deal because this was one of the first polls that showed that Grimes might actually beat McConnell. And so a lot of people referenced this poll and were like, well, look at this. We see that Grimes overtook McConnell by 2 points in this uh, little poll they had here. And so, maybe she is going to win. Then we saw about a week later, they had McConnell had 52% and Grimes had 44%. Okay. A few weeks later, right before the election, they had McConnell at 50% and Grimes at 42%. Okay, so fairly close to what they had seen October 17th. Then when we got down here, this is what actually happened. Now, I guess this would be somewhat considered the true parameter, although not everybody voted, but this would be about as close as we could get to a true parameter. So what happened in the end was McConnell won with 56% of the vote and Grimes got 40%. So you would look back at a month before and say, so did something big happen in that month to make it go from 46-44 to now 56 and 40? Or was something wrong with this poll? Well, the first thing you would look at is something that we're given in our sample polls is generally a margin of error is included somewhere, okay? That margin of error is allowing for sampling error, okay, to occur because we know that our statistic might not be exactly correct, but we're hoping that when you add on that margin of error that the true parameter is somewhere in that interval of numbers, okay? And we're going to talk more about that later. But we could use this margin of error to kind of determine, where the true P might be. All right. But basically what we want to talk about just right now is that sometimes the polls don't get it right. Right? But some of these, were fairly close to what really happened. But we're wondering, why did this one not work? Does that mean they did the poll incorrectly? Or does that just mean that it was just one of those bad samples? Here was another one. Now, this was in the spring when we were still going through the Republican primary. And so this one was for the Wisconsin Republican primary. Cruz ended up winning that one with 48%. But you see, there were varying thoughts on who was going to win. Let me erase a few of these so you can kind of see them a little better. So you do see that all of these have a margin of error on them, and that's what we're going to talk about more later on. But you see in this one poll here, they had Trump up at 42% and Cruz was at 32. This one has Cruz at 38 and Trump at 31. This one has Cruz at 42 and Trump at 32. So, you know, these, and this one is another one, 43 and 37. So most of them kind of followed that 40 and 30 thing for Trump and Cruz. That's pretty much what happened, the 48 and 35. But why did this one poll show that 42% were going to vote for Trump and only 32% were going to vote for Cruz? And this was only a few days before the primary. So this one was actually, it looks like by the date, a little closer to the actual primary than these others were. So what was it that happened? You know, what happened there? So how do we create these polls? How are we able to, or not create the polls, sorry, how do we create the statistics that we get from the polls and how do we use them correctly? So what we're going to talk about in this chapter is creating confidence intervals. So a confidence interval is an interval of numbers obtained from a point estimate of the parameter. Okay, so what you should think of is a point estimate is just one point on the line, right? So if I go out and do a poll, like for example here, when they did this poll, they said 42% were going to vote for Ted Cruz. Now, did they really believe exactly 42% of the voters were going to vote for Cruz? Well, probably not, because they understand how sampling error is. This was one sample of 742 voters. But they realize that when we do another sample, we'll probably get something a little different. And when we eventually get our large group of people that actually do go and vote, that probably won't be exactly 42% to vote for them. So since they know that this might not be the exact number, instead of using just that point estimate, what we're going to do is we're going to add and subtract a value to that point estimate and now create an interval of numbers, okay, a confidence interval is what we're calling it. And we're saying that, okay, our parameter might not be exactly equal to the statistic I got, but I'm pretty sure that it's going to be between these two numbers. Okay, so that's what we use our margin of error for. Okay, this margin of error that was given here, the plus or minus 3.5%. I'm going to add and subtract that 3.5% to 42%. So that's going to tell me that I really think that Ted Cruz could get anywhere from 38.5% if I subtract 3.5% up to 45.5%, right? So now I've got a range of numbers that I can say that's where I think the final results are going to come in. And you can see this was a little higher than what they expected, but it's fairly close. You know, that's a pretty good guess, you know, when you're guessing at that, because really, honestly, a lot of statistics is just educated guessing. Okay, we're using lots of formulas and mathematical equations and things like that to try to get to these numbers, but in the end, it is just a guess. Okay, we don't know for sure. We're never 100% confident about anything. Okay, so what is our level of confidence? Well, to figure out your level of confidence, we really just create it. We decide, you know, do I want to be 99% confident or 95% confident or 90% confident? And once we figure that out, what our level of confidence is, then we can create our confidence interval. Okay, the level of confidence is denoted by 1 minus alpha times 100%. Now you've seen that alpha before. We talked about that back in chapter 7. Alpha is always the area over to the right. Okay, so that alpha we'll talk more about in these last two chapters because they do help us to identify, you know, what area we're looking at. So once we create that confidence interval like this down here, then we'll say we are X% confident. So we're 90% confident or whatever level of confidence we used. So we are X% confident that the population proportion is between the lower bound and the upper bound that we created. Okay, so confidence intervals are created by taking your point estimate and then adding and subtracting your margin of error. Okay, we use so to use this margin of error to get a correct interpretation, we have to figure out how do I find the margin of error, right? So in a lot of these polls, the margin of error is given to you. So you may have wondered, where are they getting that number from? Are they just guessing that they're, within 5% or, how do they do that? Well, the margin of error is based on really two things. It's based on your level of confidence and then your sample size. Okay, so to find the margin of error, we need to decide our level of confidence. For your homework problems, that'll be given to you. They're going to tell you what level of confidence you want. Once you get the level of confidence, then you find the corresponding Z alpha half, okay? And that comes from our normal probabilities. That Z is the same Z that we're used to using with our, when we find the Z-score, okay? That's our Z alpha half. So let's say we want to have a confidence level of 95%. What does that Z alpha half represent? Well, for 95%, that means our 95% is here in the middle, okay? The alpha is the area to the right over here, okay, generally, or the area on the outside of what we're looking for, okay? So for us, the alpha outside of here, we've got 1 minus alpha is going to be equal to 0.95, right? Because that's how our level of confidence is written, 1 minus alpha times 100%. So if 1 minus alpha equals 0.95, then what does alpha equal? Well, then alpha equals 0.05, right? Okay, then because the 95% is right in the middle and not like shifted here to here, it's not the 95%, the lower 95% or the upper 95%, it's the middle 95%. Because it's set like that, we distribute that alpha 0.05 into both tails, right? So we divide it by 2. That's why it's called the alpha over 2, the alpha half, okay? And that equals 0.025, right? So our alpha half is 0.025. We would look up the alpha half percentage in the normal table to find the corresponding Z alpha half value, okay? So we would do that just like we would look up, any area in our normal table. You look it up on the inside of the chart, find the corresponding value. Now, our confidence levels are going to be pretty much the same. Generally, the ones we're going to use are 90, 95, and 99. So if we know we're going to use one of those three, we kind of have some Z alpha halves that are going to remain constant. Okay, so these are the most common ones that we're going to use. For 90% confidence, we're going to use 1.645. For 95%, we're going to use 1.96. That's the Z alpha half. And for 99%, we're going to use 2.575. Okay? Now you might wonder, where did those come from? Those are our normal probability charts that we're used to using. Okay? Those Z's that come from that. Remember, with the empirical rule, if we have 95% of our data, we're talking about 2 standard deviations away, right? We talked about that back in, chapter 3, I think, and then of course again in chapter 7. So 95%, we remembered that was 2 standard deviations away. Well, why does this say 1.96? Why isn't the Z 2? Well, because honestly, the Z is not going to be 2. 95% of the data is not actually 2 standard deviations from the mean. It's actually 1.96 standard deviations from the mean. Now, why didn't we say that the very first time we talked about the empirical rule? Well, when you're trying to memorize those things, it's much easier to think about 1, 2, and 3 standard deviation away than to think about it as 1.96 standard deviations away, right? 2 is pretty close to 1.96 when you're rounding, right? So it's not a big deal as an estimate. But now going forward, we're pretty much always going to use this 1.96 for the 95%, unless it specifically says something about using the empirical rule, because 1.96 is the more accurate representation of where 95% of our data falls. Okay, so thinking of how to describe these confidence intervals, okay? When we create a 95% confidence interval, what that tells us is that if I were to go out and take different samples of the same size and calculate p hat, and I were to put those in this sampling distribution, 95% of those p hats are going to fall within 1.96 standard deviations of the mean, right? Most of them are going to fall between here and here. But 5% of them are going to fall outside of this blue area, right? They're going to fall over here or over here. So when I construct my confidence interval, I'm 95% sure that I got one of those statistics, one of those point estimates that fell inside the blue area. Now, yes, it's possible that I got one that fell outside of there. There is a 5% chance that it didn't fall in this blue area, but that's a very small chance, right? So I'm hoping that my statistic that I got and then the interval that I create is one of the good ones, okay? It's one of the ones that does fall in the blue area. So that's what may have happened in some of these, okay? If they were good polls, the samples were representative of the population. 5% of the time, the statistic that we get is going to fall outside of that blue area, right? It's going to be one of those that falls far away from the true P. And so we might have just happened to get a sample that fell in one of those extreme areas, okay? And so that would mean that our statistic would not really be a good estimate of the true parameter. That doesn't mean we did anything wrong. It's just how sampling error works, okay? But it could be also likely that maybe the way we collected our data wasn't good. Maybe we didn't do good enough randomization. Maybe we didn't have a very good mix of the population in our sample. You know, maybe we happened to get a sample that was all women or all higher income individuals or higher educated people or whatever, who knows. Something about our sample may have been different from the true population, and that may have made our percentage be off, okay? But just because one poll is incorrect, that doesn't necessarily mean anything was wrong with the poll. It's just showing that sampling error exists, that sometimes you get polls that aren't very representative of the population. You can't really do much about that, unfortunately. Since the margin of error is half the length of the confidence interval, the formula for the margin of error is going to be this, okay? So this is going to be how we actually create the margin of error, okay? We take our z alpha half, which we just talked about is based on our level of confidence, and we multiply by the square root of p hat times 1 minus p hat over n. Now, what does this look like? Does this look like something you remember? Well, it should look very similar to the standard deviation of the sampling distribution, right? So when we're talking about being within 1.96 standard deviations, we're looking at that 1.96 times the standard deviation of the sampling distribution, okay? So the sampling distribution of p hat, the standard deviation of it was the square root of p times 1 minus p over n, right? Which is this, p times 1 minus p over n. But notice that we used p hat here. Now, why would we use p hat instead of the true p when we're trying to create a confidence interval? Well, if we're creating a confidence interval for P, so we're trying to figure out what the true P is. How could I plug in P here? I don't know what it is, right? So since I don't know what P is, instead I'm going to use P hat to plug in um, to my standard deviation. Okay, so I'm going to plug in P hat in place of P because P hat should be a pretty good approximation of what the true P is, right? So hopefully it is anyway. So if I don't have the true P, I'm going to use P hat for my standard deviation. Now when we went back, if we go back and look at chapter 8, when we were doing those problems and calculating, probabilities or whatever, normal probabilities, we were given the true P. So we were able to use the true P in that case. So if you have the true P, you can use it, okay? If you don't, then you use P hat as an estimate of the true P. All right. Now, most newspapers and magazine polls use 95% confidence, so they're using that 1.96 times whatever this is to get their stated margin of error. This was just an example here. You'll always see that margin of error somewhere on those polls that you look at, or at least you should, because you want to know, is the margin of error a small margin of error? So is their statistic that they're giving you, within a few percentage points of where the true P is, or is their margin of error like 20%? Because then that's not going to give you a very good estimate, right? Because you're saying, well, I could be 20% over or 20% under. That would be a very wide range. So you hope to see margin of errors fairly small. 1 to 5% is what you're usually going to see for your margins of error. Okay, now how do we calculate our confidence interval? Okay, we've kind of talked about all the different pieces, but actually creating that confidence interval. How we're going to do that is really what we were talking about here, just creating that or looking at that our statistics should fall within 1.96 standard deviations from the mean if we're talking about a 95% confidence interval. That's how we're going to create our confidence interval. So the lower bound of our interval is going to be P hat, so our point estimate, minus the Z alpha half, which comes from our level of confidence. Okay, so it's going to be most likely one of these three numbers, 1.645 for 90%, 1.96 for 95, or 2.575 for the 99%. All right. So we're going to plug those in, and then we're multiplying by the standard deviation of the sampling distribution, which since we don't have P, we're using P hat in place of P to estimate it. We're going to do the square root of P hat times 1 minus P hat over N, okay? And then the upper bound, we'll just be adding that on instead of subtracting, all right? Also remember, it has to be the case that n times p hat times 1 minus p hat has to be greater than or equal to 10. That's to make sure that our distribution's normal, right? Now, how does sample size relate to our margin of error? Okay, well, sample size, the larger your sample size is, the smaller your margin of error is going to be, which means the larger your sample is, the closer you expect your statistic to be to the true parameter, right? Because we know the more we choose in our sample size, the less variable our sampling distribution is. So we're going to expect that our values are going to fall much closer to the true P, okay? So that's one of the reasons why, even though you can maybe take a smaller sample size, to make this true or to make sure you have a normal distribution, the larger your sample size is, the better your estimate is going to be of the true P. However, when you look at this, when you go from 100 to maybe 200, you see a pretty big decrease in your sample error or your margins of error. But if you go from like 1,000 to 2,000, it's not really that big of a difference at that point, or 2,000 to 4,000, or et cetera. Continuing on, you see that it almost starts to, approach some sort of limit that it's never going to get much smaller than, right? And that's why a lot of polls kind of use 1,000 as their sample size. You may have seen some of the Gallup polls and kind of wonder, why do they only use 1,000 or 1,500 people? Why wouldn't they, they're a huge organization. Why wouldn't they go ahead and survey 10 or 20,000? Well, the biggest reason is because, it costs a lot of time and money to sample 1,000 people. And it takes a lot more time and money to do 10,000 or 20,000. So if they realize that the margin of error at 1,000 is 3%, and to get twice as many people to get to 2,000 people, they've really only decreased their margin of error, less than 1%. It's just not really worth it. To be within 3% or within 2% isn't really that big of a deal most of the time. So 1,000 people is, generally accepted as a pretty good sample size because you're going to get a pretty good margin of error for that. Now, if you only have 100 people, now you're talking about a margin of error of almost 10%, which is not really great. That's probably, I could probably guess just as well as, go ahead and calculate that data from 100 people. So, 1,000 is where most of our surveys are probably going to be at, the ones you're going to see like for the polls in the news or online or in the newspapers. All those are generally going to be around 1,000. Okay, so let's look at an example. This was a WBKO poll. Of course, not a great poll because it's an online, so we've got voluntary response and all that stuff. But let's just assume, let's just pretend like it was done in a better way, okay? But this says, do you think Matt Bevin should cut funding to higher education via executive order? This was back in the spring of 2016 that we were talking about that. And so we had 52.71% say yes, 47.29% say no. So looking at those who approved of the cuts, what is the point estimate for P? So remember, the point estimate is just our statistic. So here that would be P hat equals to 0.5271. Create a 95% confidence interval for P, right? So because we're doing 95%, our Z alpha half is going to be 1.96. We're going to take P hat plus or minus 1.96 times that standard deviation of the sampling distribution, right? So we'll have 0.5271 from here plus or minus 1.96 because of our level of confidence times the square root of 0.5271 times 1 minus 0.5271 divided by 628 because that was our sample size here. Okay, now this whole thing here in red, this whole side, what you add and subtract to your point estimate, that is your margin of error. Okay, so that is where the margin of error comes into play. All right, so we end up getting 0.0390, so that would mean our margin of error is about 3.9%, right? So we would add and subtract that to here, and that would be our confidence interval. So it'd be 0.4881 up to 0.5661. Notice when we create this confidence interval that in the middle of the interval is P, right? We're trying to estimate where the true parameter is, not P hat, right? We know what P hat is. We just got that. P hat is 0.5271. We're trying to estimate about the true P. Okay, now do a 90% confidence interval. So a 90% confidence interval, now the Z alpha half is 1.645. Okay, so this number is going to change to 1.645. Everything else is going to stay the same. Now my margin of error is 3.3%. And so I create this interval that I'm 90% confident that the true P is between 0.4943 and 0.5599. Is there a statistical difference between the percentage of people who approved and the percentage who disapproved? How can we show that the two results are statistically the same? Okay, because some people would look at this and they'd say, oh, well, a lot more people are for this than against it because about 53% are for it, only 47% are against it. Well, how could we show that those possibly might be the same? That maybe The difference there is just due to sampling error. If we took another sample, we might see more people say no than say yes. So the way we look for that is let's create a 95% confidence interval for the no's. Okay, so when we do the no's here, we plug in 0.4729, okay, because that's our point estimate for how many are opposed to this. We do that and we get an interval of 0.4339 to 0.5119. Now, if you compare this interval to the interval we got for the yeses, do they cross at any point? Do they have some common values? Yeah, they do, right? From 0.4881 all the way up to 0.5119, they cross. So like 50 is in here and 50 is in there. It's possible that 50% would say yes and 50% would say no because based on these two intervals, they have some common outcomes. So that's how we would show that two things are actually statistically the same using that margin of error. That may have been something you heard in the recent presidential election when a lot of the polls were showing maybe Trump ahead by one or Clinton ahead by one or two. They would say that with the margin of error, they were in a statistical tie. And what that means is, if you're only up by 1 or 2 points and the margin of error is 3%, that says that statistically you all are actually in the same both, you all are both about even because we don't have enough evidence to show that you are statistically doing better or worse than your opponent. Okay, so that margin of error is really important and really important to understand when you read a poll. Don't just look at the one statistic they gave you. You've got to look at the margin of error, because we know now that every statistic has some sampling error, because we took or calculated our statistic from a sample, not from a population. All right. So those numbers that came from a sample are going to have some error in them. They may not be exactly correct. So the way to resolve that is we say, well, I may not be totally confident that this is my answer, but I'm 95% confident that the answer is somewhere between these two numbers, okay? And so that's really what you need to look at is you need to combine the margin of error with your point estimate and then see, where that result leaves you because the true P is probably somewhere in here, okay, for this example. So maybe not exactly 52.7% of people agree with this. It may be more like 49% or 56%, somewhere in between those proportions. Now notice that higher confidence decreases the precision but lengthens the confidence interval. Lower confidence improves the precision. Okay, so now you have a smaller confidence interval, but you have lower confidence that it's there. Okay, so just notice as you lower your level of confidence, you're going to get a smaller confidence interval. Okay, how do we use our calculator to calculate these intervals? Okay, to do the confidence intervals in your calculator, we're going to use the 1 proportion z interval. Okay, and so to get that, let me bring up my calculator here. Okay, so to get this on your calculator, you're going to go to let me clear this real quick. I'm sorry. You're going to go to Stat and over to Tests. We haven't used this yet, but so go to Stat and all the way over to Test, okay? And we are going to do a 1 proportion Z interval, okay? It's one proportion because we're looking at one p hat, right? We've got one p hat that we calculated. It's a Z interval because we use the Z alpha half to construct our interval, right? So it's the same thing basically as saying it's a normal interval, okay, coming from the normal distribution. So this is called a Z interval. So we're going to use the one proportion Z interval. So press enter. Then you're going to get this prompt, okay? So it's going to say how many successes did you have, right? What's your X value? How big was your sample size? And then what's your level of confidence? That's what the C level is. So for ours, we had 331. I don't remember if this is this from the one we just did? Let me see. Yeah, this was from the one we just did from that WBKO poll. So we had 331 that said they do agree with the funding cuts. 628 were how many people we had in our sample. Our confidence level we always put in as a decimal. So if you just put 95 there, it's going to come back with an error. So it wants something less than 1. So you could put 0.95, or if we were doing a 90% confidence interval like we're doing right here, you do 0.9 and then calculate. Okay, and so here's your output. It gives you the lower bound and the upper bound. So this is we think P is between 0.4943 and 0.55984. It also goes ahead and calculates your P hat for you if you needed that. And then it tells you again what your sample size is, so you can kind of double check and make sure you typed all that in correctly. Okay, so you just go to stat, test, and then go all the way down to one proportion Z interval for this one. Okay, so I think I'm going to end this one right here just because I know it's already a long video. So I'm going to stop this here. We'll pick up next time looking at how to calculate what sample size we need and then doing a few more examples. Remember, if you have any questions, you can contact me at angela.galloway@kctcs.edu. Thanks.